Alright guys, so last and but not least in this unit, we're going to look at Newton's law of universal gravitation and geosynchronous satellites. So Newton's law of universal gravitation states that every particle in the universe attracts every other particle with a force that is proportional to the product of their masses and inversely proportional to the square of the distances between them. So basically, the star that is 100 million light years away basically has a force acting between me and that 100 million light year away star, and literally every single particle in the universe exerts a force with every other particle in the universe. And this can be written as F is equal to G, the universal gravitation constant, which is not the same as G of 9.81 meters per second squared, which is the gravitational constant of Earth, m1, m2, those two masses that we are looking at, over r squared. So G, the universal gravitation constant, is 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. And the reason why this number is so minuscule, and you should be glad that this number is so minuscule, is that, for example, you are probably sitting in your home, in your room, watching this video, and literally every object around you is exerting a force on you. And if this gravitation constant wasn't so small, and this force therefore wouldn't be incredibly small, since the distance between you and these objects is very small, you would be flying all over the place, since these forces would be tugging you all over. But these forces are so weak that thankfully you are not flying all over the place. Okay, so now we're going to apply this, and we're going to apply it to our idea of centripetal acceleration and finding out that acceleration and the velocity and the height of a geosynchronous satellite. We're going to do the same exact thing that we were doing in the previous sections of this unit. So imagine that we have a fish-looking satellite orbiting the Earth in a perfect circle, and this is geosynchronous. And a geosynchronous satellite is one in which it is above a certain point of Earth, and it is always above that certain point. So what does this tell us? This tells us that the period of a geosynchronous satellite, since it is directly above that same point, is equal to 1 day, since it will go around a complete orbit at the same rotation of the Earth, and since one whole day or one whole rotation of the Earth is 24 hours, so is the period of a geosynchronous satellite. So now, with only knowing that it is a geosynchronous satellite, you can find both the height and velocity of the satellite. That's all you need to know. So now let's look at the actual satellite in the diagram. You have this force which is acting directly between the two radii of two particles. That is the key. Since it is acting between the two radii, in this case being the Earth, the radii of the Earth, and the radii of the satellite, and we're assuming that all other forces acting around with other planets, other objects, is negligible. We can equate that to our mass times radial acceleration. Since it is a radial force acting towards the center of the circle, right there, as you can see, we can equate it to mass times radial acceleration, which is what we did in the last 4 or 3 examples that we did. So now we're going to write our summation and the force radial, and the only force that we're assuming is acting on it is the G, m of Earth, m of satellite, over r squared, and that's going to be equal to the satellite's radial force, which is mass satellite times v squared over r. And now we just solve and plug in numbers. So right off the bat, you can realize that you can cross off the mass satellite since it's on both sides of the equation, and that means that the mass of the satellite does not affect our height nor our velocity. So we can also reduce, since if we multiply both sides by r, that would just cause this to be r and this disappear. So we have v squared is equal to gme over r. So gme over r, which we'll move that to the other side of the equation, is equal to v squared times r. Also, now we can't go on. Since we know the gravitational constant and the mass of Earth will be given, the mass Earth is 5.98 times 10 to the 24th kilograms. We need to figure out how to get rid of the v. What did we talk about in the first video? We know that velocity is equal to 2 pi r over period. And since we know the period, since it's geosynchronous, it's equal to 1 day, and pi is a value, and we are given the radius, or we are trying to find the radius, which is the height, we can plug that in. So we have g, mass of Earth, is equal to 4 pi squared r squared times r. I just squared 2 pi r squared, which would be 4 pi squared r squared times r over t squared. And so then you get r cubed is equal to g e times t squared over 4 pi squared, and you can take the cube root of that to find the radius. So that means our radius is equal to the cube root of gme, which is 6.67 times 10 to the negative 11th newtons times meters squared times kilograms over kilograms squared times our period, and we convert that to seconds to get our units. 1 day is 86,400 seconds. If you don't believe me, do some stoichiometry, and if you're wrong, that means you're wrong. Squared over 4 pi squared, and you get a radius of 4.23 times 10 to the 7th meters. But hold on, this is a radius. This means the distance between the radius of the Earth to the radius of the satellite. We want to find the height. So therefore, we have to subtract the radius of the Earth to find the height of the satellite, because this is including the radius of the Earth, and the radius of the Earth is 6,380 kilometers. So we would subtract 4.23 times 10 to the 7th minus 6,380 times 10 to the 3rd to convert it to meters, and we get 3.59 times 10 to the 1, 2, 3, 4, 5, 6, 7 meters. Let me make sure of that. 1, 2, 3, 5, 6. Yes. So there you have it. That is our height. And don't worry, the radius of the Earth will be given to you. Even on an AP exam, the mass of the Earth will be given to you. You don't have to memorize it unless your teacher is very evil. And then we want to find the velocity, and that is very easy. We just look over here, and we know that v squared is equal to gme over r. And we already found the r. But remember, the r is not the height, but rather the radius between the center of the two. So we can't use the height of the satellite above the Earth, but rather the distance between the nuclei, even though they're not really nuclei, the centers of the two particles. So we have v is equal to the root of gme over r. So v is equal to the root of our constant, 6.67 times 10 to the negative 11th times mass of Earth, I'm not going to write that out, over our radius of 4.23 times 10 to the 7th meters, and you get a velocity of a whopping 3,070 meters per second. How about that? Okay, thanks for watching this entire unit. If you have more questions, visit us at SIG Studies on Twitter. You can send us a DM. Our DMs are open. You can request anything from physics to chemistry to calculus to math SL. Literally, send me anything that does not include rocket science, and I will try to get a video or a worked out solution for you. And also don't forget to click that subscribe button. Comment, did this help you? Did this not help you? And see you later.